Welcome to the AI and Big Data and Finance webinar. We are delighted to have two excellent speakers today. So Nancy Wallace from UC Berkeley will present her paper Convolutional Neural Networks and the Wildfire Risk of California Residential Real Estate. Our ABFR co-organizer, Maryam Farboodi from MIT Sloan, will be the discussant. Nancy will have 30 minutes for the presentation. If there are any clarifying questions in the Q&A, I will briefly interrupt her after 50 minutes to answer those questions. Maryam has 20 minutes for her discussion. Afterwards, we open the floor for questions from the audience. As audience, please submit your questions in the Q&A. We will then call on you during the questioning part. And as a reminder, please be respectful with your comments. The presentation and discussion will be recorded and together with the slides posted on our website. After the main part of the webinar, we will have an unrecorded discussion where everyone in the audience will be upgraded to panelist. Nancy, the floor is yours. You have 30 minutes.
Thank you all very much for having us. We're really looking forward to this discussion and the opportunity to present this paper, which is very new on the ground, and we're really looking forward to comments. So we've been working on wildfire events in California. We're economists, and the view is really how to think about pricing them, looking carefully at the regulatory structure, which is part of the problem in California, and of course the ever-increasing levels of both numbers of fires, severity of fires, and losses associated with fire. So what I'm going to talk about today is the regulatory and climate risks of the property and casualty insurance industry's provision of residential single-family coverage for wildfire perils. We're going to talk about some new methods to measure annual wildfire propensity and the losses given wildfire in residential housing, and then conclusions, because this paper is intended to provide us the wherewithal to predict accurately probabilities of occurrence so that we can go on and think of other innovations that are needed in the bond markets to help alleviate some of these risks, especially mitigating the risk through renovations of the homes. So I don't know how many of you are from California, but we have a number of self-inflicted threats and wildfire insurance in California. This has been in the national press, so this is not really news. And of course, it's the big Malibu fire, which I think is going to be put out very soon. One of the major problems in the state is that the major insurance companies, including the largest, State Farm, is not renewing policies at very, very large volumes, ever increasing volumes. Just between 21 and 22, they dropped 428,000 policyholders from what's called the admitted market. So that's the normal market of private firms, and forced these people into what's called the residual market, or the insurer of last resort, which is the California Fair Plan, which is not a well-capitalized operation. And if it fails, the current insurance policy payees will have a surcharge on their premium to bail them out. So the whole system is very fragile. There are some unique issues in California having to do with regulatory constraints that are going to be very relevant when we start talking about models. Historically, since 1989, and something called Proposition 103, as you know, we govern ourselves by propositions in California. The California Department of Insurance has prohibited the use of actuarial models for pricing fire peril risks, which may surprise you all. And basically what they use is they use the historical 20-year average experience of each firm. So very reliant on means. And it's also a rate regulated industry, as it is in most states. And the cap was 6.999%, anything less than 7%. Anything greater than 6 would require a public hearing. So most of the firms would ask for 6.99 multiple times. And this whole system broke in September of last year with people asking for 30, 28, 27 rate increase approvals. And of course, the problem, what you see on the figure on the right, is that the performance of the firms in California with these issues has been very poor. So this is a figure showing you the realized loss rates for fire peril in California, and they exceed 100%. And this is happening more and more frequently. And this coming year has been especially problematic, and we'll talk about that in a minute. So overall, the direct underwriting profit in California is minus 13.1% for the underwriting of fire peril, and leading many of some insurance to leave outright and other insurance companies to threaten to leave, and which has led the CDI to respond. And the responses have been, all right, we'll consider actuarial pricing, and B, we will consider much higher rate increases. And that all has come to pass and will occur, the rate increases in particular, at the end of this month. So we're weeks away from it. And then the use of actuarial models is also going to be allowed as of the end of this month. Again, we're weeks away from these very, very major changes in the market. So the wildfire patterns in California are very much driven by meteorological features. And importantly, the most important feature, we'll see this in various guises as we go through the talk, is maximum temperature. And some of the climate research looking at the increasing heat and also intensity, especially in certain topographies of these fires, are showing increasing sensitivities to increases in max temperature on a given summer day or in a series of days to increases in wildfire occurrence. And a maximum temperature is, not terribly surprisingly, highly correlated with other meteorological, vegetative, and topographic features. And so having all of this correlation is sorting through these preconditions of fire is a challenge, and there's a huge climate literature that looks at various aspects that's growing ever larger. So the graph shows you how upward sloping and steep looking this is. Obviously, it's over 100 years, but basically we see a very relentless upward progression of max temperatures in the Western states. So the other feature that's important is there's a very important time varying distribution pattern of wildfires in the state. And so I'm showing you from 2002 to 2017, and in these various brackets that we're showing you, as you can see, the incidence of fire and the size of these fires has dramatically increased over this period. And it has a great deal to do with where the heat is, which is in what's called the Great Basin. So this is Nevada, and how the heat drives the winds across California. And it's going to be, we'll see, there's a large difference between Northern California, everything north of the Bay Area, and Southern California, everything south, roughly, of the Bay Area. And basically, most of the fires historically have been in Southern California. And what's really the news in the state right now is the Northern California incidence of fire. And that has to do with two very important winds that we'll be seeing in the modeling. The Diablos, which are the winds in the north, which were considered to be 100-year risks. And we've completely revised that view of these winds. And then, of course, the fire in Malibu right now is a Santana fire. And the Santana winds are different. They all start in the Great Basin, but they have very different physical properties. So, given this situation with the serious problems in terms of profitability for the P&C carriers, accurate prediction of wildfire occurrence, which is what our focus will be. There is another whole literature that looks at the growth of fires. So that's the physics literature. What's the physical dynamics of fire? But we're going to be looking at occurrence. But understanding these occurrence events is key to pricing and eligibility decisions. And as I said earlier, in California, that had been restricted to backward-looking means, which has led in many ways to this very inaccurate pricing scheme that homeowners are facing and the industry is facing. So what you need to do this correctly is very granular, both spatial and time series measurement of surface preconditions following the climate literature. And so what we've done is we've grid celled out the state into roughly 94,000 plus cells from 2000 to 2021. Our original data is in a 4 kilometer grid, and we interpolate on the daily data. We have both hourly data and daily, so that we're dealing with 2 kilometer grids. And then we're going to map, think of each grid point as the center of a kernel. We'll map 6.9 million houses over that grid. So the climate variables we're looking at are measured point in space. Some of this is raster data. You should think of these cell grids as basically like pixel data, because that after we put this all together is essentially what they look like. Some of our data is hourly measurement, like the wind speed, duration, and direction. Some of it is daily measurements, such as specific humidity, maximum air temperature, dry lightning, and then some of it is fixed, having to do with vegetative coverage, the transmission grid, and the utility districts. We have several very problematic utilities that haven't maintained their infrastructure. So there's a lot of heterogeneity, as you might suppose, in a Mediterranean climate like California. And so all of this heterogeneity is going to establish these preconditions with the treatment of the meteorological factors. And of course, they're also very highly variant on the topographic features. Importantly, the Sierra Nevada, which is on the eastern border of California, and then the coastal range, which is on the Pacific border of California. And so we have very important heterogeneity, and the key things are the various types of forest, and then in Southern California, the chaparral, very densely covered shrubland that is incredibly flammable as it dries out, as is the woodland forest of the north. There's also a lot of heterogeneity, even in maximum temperature. We have a huge desert region that we have to account for that is very hot. And then also the Central Valley is very hot. But as you can see, the Central Valley is irrigated, very green. And so accounting for all these interactions of vegetation and water really are going to matter. And so these are pretty high dimensional feature spaces in terms of understanding the phenomenon. So what we're going to propose is the use of spatial temporal dependence. Just the ridge lines of the mountains are going to introduce a lot of dependence, because ridge lines, slope, aspect are all going to really matter because they're so affected by max temperature. So we're going to look at spatial dependence around every grid cell. So we're predicting occurrence. So Y is the occurrence of fire at a grid cell point or a grid cell node. And then we'll look at the cells around it. So we'll be looking at kernels of various sizes around these grid cells. And then fire, or the treatment of temperature, has an aggregating effect over time. And so we also want to control for the temporal dependence at the grid cell level. And so we're also looking at the time evolution pre-treatment features that lead to fire, are some of the preconditions of fire as well. So just background, fire is mostly caused by human beings. Other than dry lightning, which causes about 20% of the fires, most of the fires are some interaction of humans with these preconditions, like a Tesla accident where the cars burst into flames, or people riding their dirt bike in the grass and other friction causing fires. Okay, so how did we get here? We've tried lots of different methods. We started just looking at each cell and its time series was its own independent time series, and then looking at vast numbers of time series using PCAs and kernel PCAs and directed graphs. We've been down many roads. But we think that spatial temporal convolutional neural nets really proposes a tool or offers a tool that's appropriate to the nature of this problem, which is so close to the visual pixel problem that these models have been shown to be so effective for, and also uses with videos where you have both the time dimension evolution of those visual features. So their benefits are they can automatically extract important spatial and temporal features from the data without relying on handcrafted features. And that has to do with the heavy use of logistic regression or generalized linear models or various kinds of other kinds of models where you have to use many, many, many interactions, handcrafted. Also, the CNNs can learn the motion patterns in time series data and fully use these patterns to account for past influence and future predictions. They also allow for complex functions that are needed to accurately model these joint spatial correlations and temporal dynamics. And they can easily handle the cell adjacency problem, that occurrence across cells propagates cell by cell. And so controlling for these really important spatial features is something that's very important, as well as the cumulative effects of these phenomena. So multiple days of treatment can lead to higher preconditions. And then lastly, handling the correlations which we know exist, especially given that so much of it is being driven by max temperature. And this is a very nonlinear parameter space. So as I said, we are going to think about both the spatial correlation as well as the temporal correlation for the event space, which is the occurrence of wildfire. So our goal is, long run, to price insurance. So we would like to get out of sample forecasting. Insurance products are annuals. And so our goal was a model that would give us at least a 1 year ahead accurate out of sample forecast for the occurrence of fire. As I said, in California, we've been using historical 20-year means. So clearly this will be an improvement on that, at least we hope so. So our sample is from 2000 to 2020. And this is just an example of how we set up the data. So this is an example of a 3D CNN with a kernel size of 3 periods in the temporal and a 5x5 grid of the feature space across the various hourly, daily, and fixed features that I showed you at the earlier slide. And so this would be a 3 temporal convolution size past 3 days with a 5x5 grid of the feature space, and then measuring the fire potential of a specific cell, which I'm showing here in orange. One thing that I'm not showing in this schematic is that we do customize the CNN filter to prohibit the look ahead problem. So that's been something we've been very worried about. So just to give an overall, since I have a short time, idea of how this model works, our input vector, we branch the data into daily meteorological inputs that we're measuring over 365 days. So this is the temporal component. And some of these are measured hourly. The wind measurements are an indicative over hourly measurements, 2 a day. And then some of them are measured daily, again, on 2x2 grids, 2x2 kilometer grids. So our daily meteorological data is a 3D convolution where we're going to be looking at the maximal fire potential over each year. So what our goal is to have an annual prediction out of sample. So we're taking the 365-day data and its feature space, and we're looking at a max pooling for the maximal annual fire potential over that year. So that's one branch of our model. Our second branch are the fixed cell characteristics, and those are fixed features, things like topography, the vegetative coverage, the slope, the aspect. Those are things that are essentially fixed. And so that's a 2D spatial convolution. And then we concatenate these two convolutions. The one is in the fixed characteristics, the other in the very dynamic characteristics, which are measured as a maximal for a year. And then we concatenate those to a 10-channel feature space, and then fully connect these layers to predict the out-of-sample annual fire probabilities by cell. So that's our goal, to get one period out of sample using 3D convolutions in the meteorological data and 2D in the spatial. The weights, of course, are the same in both, and that's something when we talk about tuning that has been a focus of ours, because this is somewhat early days on this paper, actually quite early days. So not terribly surprisingly, fire is a relatively rare event in a 94,000 cell space. And so in our training data, the incidence of fire is about 1.65% of the cells have fire occurrence. So the data are very imbalanced. And my co-authors and I are very used to working on mortgage data, which is similarly very imbalanced. Default is actually a very rare event. And this is similar, only even more extreme. And so we've been really focused on the loss function and thinking about our weights, because as we see when we get to looking at the results, we are very likely, our tuning focus is going to be very focused on these weights. Right now, we are not using time-varying weights. And so thinking about future tuning, given the important data imbalances that we have in our data, is basically our focus and effort right now. So we're looking at thinking about the focal loss formula, thinking about specialized loss functions to try to penalize the easy to classify non-existence of fire or incorrect forecasting of the occurrence of fire. And likely we're going to be moving to time-varying weights. We think that time-varying weights will themselves be revealing and help us understand interesting dynamics, maybe through using solvency saliency maps. And lastly, precision recall trade-offs. Interestingly, when we look at the results, we'll see that the objective function of the insured may be very different from the objective function of the insurance company, and the ability of these models to deliver for one over the other group of policyholders versus those selling the policy is going to be important. So quickly to get to the results. So the out of sample 1 year ahead. So the benchmark model is logistic. Logistics are used a lot. They're used in economics a lot. They're used in a lot of the models that are used in climate science, along with various kinds of gradient boosted neural nets. So the logistic model is our benchmark model. And then, so different from what I'm showed you here, which is the 3-dimensional 5-5 feature space, the kernel and the weights. We're going to compare a 1-1, a 3-5, and a 7-7. And again, our validation is, our training is from 2000 to 2018. Our validation is, we're forecasting 1 year ahead, so our validation in the data is 2019. Our validation in the forecast is 2020. Our test in the data is 2020, and our test validation 1 year out of, our test 1 year out of sample is 2021. So as you can see here, we have a very serious problem with false positives. We're estimating a very high level of false positives. Our precision is very low. About in the test 2025, the out of sample wildfire prediction is quite low, and but our recall is actually quite high. And for the good news is that we accurately predict, or we're quite accurate in the prediction of wildfires, hence the high recall, but we're seriously at risk with the false positives. And so from the insured's vantage point, especially with these very large premia increases that are going into effect in 2 weeks, 30% on average, about 27% increases in premia, this inaccuracy is a serious problem for the insured. So the F1 score is also quite low by kind of normal standards, but relative to the incidence of the events, we're optimistic about this. I think our work is really cut out for us in terms of various methods, as we were talking before, and looking at the loss functions of improving our very high levels of false positives. So basically what the model seems to suggest, and this is also an issue in the time series because of this relentless increase in max temperature, perhaps the more informative part of the data is the more recent fire seasons, but the model predictions are reasonably accurate in the high fire years, we'll see that in just a minute, but are less reliable when they're applied for periods where fires are more rare, which is what most of the training data are. Because as I said, that's 2020 through 2018. So maybe we should change the way we do do various kinds of over prediction or over sample, or perhaps more focus on the end of period. So obviously the model has its limitations vis-a-vis the insured, and in terms of accuracy of prediction of the true positives is a challenge right now. So that's our focus. In terms of feature importance, we see the features that we expected. Some of these features have fairly normal distributions. Many of them are very imbalanced themselves with very strong right tails. And so we are seeing SNN or CNN as a feature space with challenges itself. And the CNN is probably a suitable tool given the nature of the features that we're using. Again, in the test, as expected, max temperature, slope, daily specific humidity are extremely important as we shuffle the features in terms of the effects on F-score, precision, recall, and loss, as expected. So now we want to have this model give us some answers. So in terms of looking at how well the model forecasts both out of sample 2021, so that's our test out of sample. Interestingly, we basically nail some of the biggest fires that happened in 2021. This seems to be the strength of the model, of picking up the heavy fire season forecast from 2020 forward, and the 2021 forecast and how well it maps on the actual realizations of fire in most places has been quite high. And then in 2022, we then forecast 1 year ahead, again to 2022. And again, which was 2022 was a much lesser severity year. And our model seems to be reflecting that, especially in the High Sierra and in the Diablo winds. It seems to be accurately predicting those preconditions and therefore the lesser degree of fire that actually occurred in 2022. We want to map this to the built space. Insurance is about protecting real estate or protecting the banks that put mortgages on real estate. So we have a lot of real estate data, and we're estimating the losses given wildfire. And the background loss, as you can see, is about 28%. But then depending on the characteristics of the houses, and for all this, we have very extensive data set at Haas. We know the characteristics of all the houses, and building age is a very important feature, especially properties built before 2008 building code changes in the California, and building age, and then also houses that are on elevated slopes and have a lot of housing density. So taking that, both the probabilities of wildfire, and then looking at the risks, what's at risk from these fires once the fires occur, our estimation for single-family residential assessed value. So what we see in the data is when a fire occurs, the assessed value of the property goes to some number that's less than what it was before, including 0. So we can measure what these losses are. And what we find is that with our forecast out of sample again for 2021, the forecast for fire, given the effect of fire on the built space at the grid, is about $10.8 billion. That was our expected forecast. And what the actual total premium loss of fire peril insurers in the state was about $12.3 billion. So we're in the ballpark of picking up what these loss measures are, even with our outstanding task of tuning the model. So interestingly, just anecdotally, what this means for individual insurer. So State Farm is the largest insurer in the state. It experienced, as very similar to the graph that I showed you earlier, it experienced a fire peril loss ratio in 2021, which is our out of sample forecast year, of 144.8%. So a spectacular loss. This is the largest insurer in the state. It's one of the largest insurers in the United States. AM Best, which is the rater of the large insurance companies, immediately downrated State Farm to B, which makes it very much at risk for insuring properties that go to the GSEs because they need A-rated insurers. So it's been largely in the newspaper, immediately went to the state with their demand, which they're entitled to in our dual system, to non-renew 70,000 policies. 23,480 of those are on single-family residential homes. And so those are scheduled to occur right now. And so what we did is we obtained those data. We're probably going to use FOIA to obtain more information about all of this, and then compared it to what our forecast would be in terms of forecast at the zip code level. In other words, we're aggregating our grid cell data to zip code level forecasts of a likely propensity of wildfire, and then comparing it to the non-renewals of State Farm, the largest insurance company in the state that we know at least a little bit about the models that they're using. And what you see in our high propensity wildfires, their non-renewals are not as high as you would expect them to be. And even more interestingly, when we look at not just the non-renewal counts or frequencies, or if we look at the losses, so we're looking at the combination of our out of sample forecast for the likelihood of fire, again, in these very high risk areas, some of these are zip codes around Lake Tahoe, the actual non-renewal rates almost look random, suggesting that maybe part of State Farm's problem is the models that it's using or the inaccuracy of the models that it's using. And that brings us back to the policy issue in the state of California. Given that actuarial models have not been used in the state, the actual vetting of these models that are going into effect in 2 weeks isn't in place. So the actual process to vet the models, there really is not an oversight reality right now in understanding what these models do and understanding, as we've been doing, and looking at the actual deep performance of the models. So to conclude, we are feeling quite optimistic about the viability of these models for this application. The risks in California are rising rapidly. These are really challenging data sets, given the very important imbalance. In many dimensions, these actually are very heavy-tailed distributions. California has a self-inflicted regulatory problem because of the way it's regulated fire peril insurance. With the new flexibility and modeling that starts now, it seems like now is the time to be exploring new models, new applications for this problem, vetting them, getting comfortable with their strengths and weaknesses. And likely there is a very big need in California for some kind of oversight and vetting process that exists within the California Department of Insurance or jointly with people working on these problems and the CDI. So we are feeling fairly optimistic about proposing spatial temporal CNNs as a viable wild occurrence modeling strategy. To our knowledge, it's only been used in one paper on visual data in Italy, and it was only a 2D problem they were applying it to. So we feel that it performs quite well in accurately accounting for the spatial and temporal dependencies in wildfire. It also can account for the correlations between neighboring data points in a time series. It can account for the cumulative effects of these climate features, and perhaps part of a longer term out of sampling forecasting effort will be a combination of CNN and LSTM type architecture, but at least this gives us a beginning point, and that it's suitable at least for the annual contracting, which is the insurance problem for annual out of sample forecasts that are needed for insurance products. So I will stop there. Thank you.
Thank you so much for this fantastic talk. Maryam, you are now discussing the paper. Right, we can see your slides.
Okay, great. So I'm really happy to discuss this paper, and luckily Nancy did a great job discussing the paper. So let me admit that it's very hard to discuss very multidisciplinary papers, because you need 2 discussions. Okay, so you need like 40 minutes. So I'm not gonna do full fairness, but I'm gonna try to just focus on what I think might be useful for the authors and for the audience. I want you not to go into this discussion, as this is a fair and square discussion of the paper. So let me start by just kind of summarizing what Nancy mentioned, which is basically, to me, the way I see the paper is answering this bigger, is contributing to this bigger question of, can advanced machine learning techniques meaningfully improve our prediction for economically relevant questions? And in particular, of course, we need to know what is the economically relevant question. And in this paper is focusing on wildfires, which are very costly, which is something that is important in economics cost. And they have also become more frequent. So price of fire insurance in like economic terms, price of fire insurance have gone up, and even availability of insurance has gone down, as Nancy noted. So now, okay, so this is the economic question. So now we need a mathematical model for it. So what can we adopt? Very often, the literature has used logistic regressions, and they show very clearly that they are horrible. So they suggest an alternative model, which is spatiotemporal CNNs. And then, okay, so the beauty of the paper is that I think after they suggest this model and they adopt it, they actually go back to the economics, okay? So it's not only adoption of this technique in this question, they go back and look at how does this perform, in particular, how the predictions compare, for instance, with realized availability of insurance. So I do think that this is I kind of do think that this is the right way of thinking about adopting techniques in new fields. So as I said, I think I've been saying is that this topic is really, really dear to my heart. So what does the paper find? They find that the spatiotemporal CNN outperforms logistic regressions to predict California wildfires. And this despite the fact that even the CNN, the spatial temporal CNN does not have a great performance in, like, for instance, F1 score. And the complication that they point out that I think is very, very real is that fires are rare events. So like, if you want to think about like linear regressions, we try to like cut the rare events, okay? And like logistic is slightly better than that, but not so much better, okay? And then the other thing that I think is very important is that there is a possibility of non-stationarity and trends, especially now, okay? So then they find that when they put back the model into and find the economic predictions of the model, translate the predictions of the model into economic terms, they find that the estimates are consistent, and sometimes they find inconsistent with the insurance company's State Farm withdrawal from some local markets. And if I get there, I will give like my opinion of that, but that's okay. So what I'll do is that I'm gonna briefly talk about paper insights. Luckily, Nancy did a great job, so mine is gonna be very brief. Then I'm gonna, the main part of the talk will be neural network predictions that are used for prediction. And in all honesty, none of this is my work. It all comes from basically computer science and statistics literature. And I'm gonna point out papers who have done it. And then I'm going to give a few final comments, which are more about using this method in economics. So let me start with the paper insight. The simple facts are that wildfires are extremely costly in California, both in human life and in loss to real estate and infrastructure. Also, then the second point is that the distribution of fire-burned areas is that very skewed to the right tail. The extent that it's close to a very skewed Pareto distribution. So, and that's just because fire is a rare event. So this poses like a bunch of economic challenges. So basically the fact that it's very costly to real estate and infrastructure means we need to have like a market for it. But the rare event nature of it causes a bunch of issues for accurate statistical forecasting. In particular, when you want to design risk management strategies for the state, for the insurance companies, we have to take care of both time series and special dependencies. So one thing is like, okay, so these insurance companies have to talk about like value of risk management. And then for the value of risk management, we need to have probabilities, and we're very bad at predicting those probabilities. Then, okay, you want to diversify and securitize wildfire risks. Okay, but so you need to know correlations. And that, again, depends on time series and spatial dependence. And as I said, linear and logistic regressions are awful for rare events because rare events are outliers. So then how does that so these were all statistical challenges. How does that feed into the economics of it? It feeds into the availability and pricing of insurance in California. Why? Because look, insurance companies need to remain solvent. So they need to have enough capital to pay losses, even in the catastrophic events. And then they face all sort of regulatory constraints, like they cannot earmark capital to certain events, and there are tax things, and there's like a million other things. There are rent setting limitations that is little by little being relaxed, but we are still far from there. And then access to state-of-the-art wildfire models are one, very costly, either developing it or like getting it from somebody, and it's very uneven across insurers, which hurts the competition. So all of this has led to unavailability of insurance in certain areas, in particular the example that Nancy mentioned, which is State Farm has withdrawn from a bunch of zip codes, at least in some services and some products, in March and June of 2014. So the solution that they propose is the spatial temporal convolutional neural networks. So what is a CNN? CNN is a deep, means multi-layer neural network. It consists of two groups of layers. The first group are linear layers that do feature detection. So we want to predict something outcome. We want to understand what features in the data, and we have huge data with 1 million features. We want to understand what features of the data are important for this particular question. Okay, we allow multiple features, and effectively each feature is a dot product, okay, of some weights with some of these characteristics of the data point. Then the output of these linear layers go into some nonlinear layers, okay, which add nonlinearity, which is kind of better than, which improves, like, even technically in the simplest way on like things like linear regression. So CNNs were traditionally used for special feature detection. So they were traditionally two-dimensional and used for image processing. And they're like really, really prominent image processing now. So what the paper does is that it adds a third dimension, which is a time dimension. And that's like what I call STCNN, because I didn't want to write spatial temporal everywhere. Okay, so it's like just, so there's like 2 dimensions of location, and then of neighborhoodness, and then 1 location of time. And it turns out that, I mean, this is something that is very well known in the literature in computer science, that like the CNNs with a time dimension are best suited for short duration time series dependence. The reason is that the weights are constant, okay? So basically when you have a 3-dimensional CNN, you're the same way that you're weighting like vegetation in the next, in the state right by you, you're weighting like yesterday versus the day before yesterday, and so on, the same all the time. So if you think that things are non-stationary, that might not be perfect. Or you think if there's long-term trends, again, that is a little bit imperfect. So Nancy mentioned this, and she did a great job. So let me just say that they actually do 3-dimensional CNN, which the 3 dimensions are time and 2 dimensions of space. And then they find features in the linear level, then RLU, and then they maximize over the month and the year, and they find a bunch of features, sorry, channel means feature. And then they augment this with a 2-dimensional CNN, which only focuses on non-time varying characteristics, which are like vegetation, elevation, things that don't change. Okay, then they find features of that, and then they augment, they join both features together, and then they kind of basically at the end they use their last step, and then they interpret that, they translate that into the annual fire probability by cells. Okay, so if you want to think about their model, it's a 3-dimensional time space CNN and a 2-dimensional space only CNN. And I will, if I get there, I actually do have a question about that. So now, what do they find is that after optimizing on the spatial and temporal dimensions of this, and you have to optimize on that, you can always go infinite, and then you can't compute anything. Okay. So they use the main measure that they use is basically about, because they do a one-to-one prediction, is basically whether they do one of the things that they're in their main specification, they try to predict whether this location is fire prone or not. Okay, so it's a binary outcome. So looking at false precision and recall is great. So the you can F1 statistic. F1 statistic is basically minimized when false negative and false positive errors are minimized to 0, and the optimal value of F stat is 1. Okay, the minimum is 0. Okay. So then the best spatial temporal CNN variant, when they tested on their test sample, its performance on F1 statistic is 0.15 or like 15%. So one thing that got me very surprised and got me to a lot of my comments is that the performance actually falls a lot between the validation and test sample, although they're just 1 year apart. Okay, and that calls for a lot of like non-stationarity or issue of like valuing the time similarly. Okay, then still with all of these issues, their spatial temporal CNNs significantly improve on logistic F1, which is about 0. Why? Because and it also improves on many other things, except basically the true negatives. Okay, and the accuracy, and the reason is that logistic is close to random. It's basically the F1 is 0. Okay, so it's close to random. So but this model do predict some negatives, so it is an issue. So then, lastly, going back to all of this was technical. Lastly, going back to the economics of it. They find that actually what the model predicts in the wildfire expected probability is consistent with wildfire, with withdrawals of State Farm from zip codes. What they their view is that is inconsistent is the distributional decision of State Farm, not very consistent with the predictions of the model, which I have my own, I have a little bit of doubt of, it's just an interpretation. All right, so with that, let me talk briefly about this notion of neural networks for protection. So, as I said, my focus would be that both spatial and time series dependence and the costly events are rare, and these are very costly events, which are rare events, and they might be, they might not be stationary. So, I think a bunch of literature worked on this, okay, in computer science, and they mostly use LSTM, sorry, not LSTM, LSTM network, long short-term memory, and they use self-attention basically and that's very much used in transformers when there's a lot of zeros, which is what Nancy is doing. And some of them augment an LSTM with a pre-feature extraction by another network. Okay, so let me just mention a couple of them, which are about the long short-term memory architectures. The first paper, this paper has like 10,000 citations. Okay, so this is the paper that introduced convolutional LSTM. So LSTM traditionally is only for time series. It puts different weights on close outcomes versus far outcomes. But then somebody noticed that, okay, maybe we want to do, so the application is for precipitation forecasting, okay? And which is kind of similar to fire. So what did they do? They made this convolutional LSTM, which all they did was that the matrix multiplication in the first layer is replaced with convolutions. Okay, so it allows for like spatial relations. Then the same authors basically use this for now, again, for precipitation, for nowcasting, and they introduced a different model, okay, which works better, which is called TrackGRU, which works better for dynamic spatial connections. And then they have their weighting scheme is now slightly different. Again, this is about weather. I mean, most of the computer science part is on weather. Then there was another paper a little later. These are in order of like that they were like the paper was written. So it was basically done that basically allowed a little similar to what they're doing in their spatial temporal convolution to allow long memory for different points. Okay, so then they have this spatial temporal memory flow with memory flow across states. And again, application is weather forecasting. And the last one had thought about non-stationarity, okay, which might be something of interest for them, which they have to have a different memory structure. LSTMs are mostly about memory structures. Okay, so this one needs to adopt it to allow for non-stationarity. And the important thing is that it separates slow varying and fast varying components in spatial data, which might be very useful for even for regulation or something like that for wildfires, again, for weather forecasting. And then lastly, let me say that this has also been adopted for wildfires. All of these are again, sorry, not LTSM, LSTM, in LSTM networks. The first one is about, this one is about wildfire predictions in Canada. Okay, so these are forest fires, so slightly different, might be useful. Then the second one actually uses exactly convolutional LSTM for wildfire dynamics. Okay, and interestingly, they compare it with CNNs. Okay, and they find that convolutional LSTM mostly overperforms, but in fairness, they're using simulated data, which is different. And the last ones are predicting hourly particle per millimeter, okay, for in wildfire prone areas, again using this spatial temporal transformers. And they actually are focusing on this 19 station locations in greater Los Angeles area. So to some degree, it is comparable. Okay, and they incorporate the sparse attention. So the rest are just like final comments with the authors, and I'm gonna share the paper with Nancy, share this with Nancy. So because I'm already out of time. So thank you.
Thank you so much. Given that we are quite late, I would suggest I will read out one question from the audience, and then we move to the unrecorded Q&A part where we can ask more questions and where Nancy can also comment on the discussion. So we have one question in the Q&A by Hyunwoo Wu, and the question is the following. So there seems to be a problem with the low precision, and he proposes there are two ways to address it, and both are related to weighting, respectively sampling. So over or under sampling essentially can trade off how you get better with one score, but you might get worse with the other score. And
Right.
I think equivalent to over or under sampling is weighting. It's essentially the same thing. Weighting is the objective function. And that comes back, I guess, to your point that you are fine-tuning the weighting functions, right? If I understand it correctly.
Yes. So it's a really fair question. It's exactly where we're focused. But Miriam's suggested papers, we may start there. But I do think this is a relatively straightforward next step of using oversampling, looking at the weights. Having time varying weights might be really interesting in and of itself. So I appreciate the question, and that's definitely where we're going. We have a lot of tuning to do.
Okay. Now, before we go into more Q&A, I would like to make an announcement. Right now, we are heading into the winter break, so please stay tuned. We will keep you updated, and we will have more exciting webinars starting after the winter break. Now we are going to upgrade all the attendees to panelists, and we are going to continue the Q&A part.